take notes.
All right, here we go.
Going to a game on Wednesday?
Is it Wednesday? Wednesday?
Wednesday.
Oh. I don't know. Excuse me? Oh. All right, ladies and gentlemen, here we go. So we're going to start off with a directed line segment. Now, one of the things we know about rays, line segments, and lines all the way from geometry and even before that. Today, we're going to take a look at kind of the directed line segment. So where the direction of the line segment is important. So a line segment to which a direction has been assigned. So a directed line segment, a direction has been assigned. Give you an example. So let's say we have some line segment PQ. So the arrow here points to the direction of this line segment. So we have a line segment that goes from P to Q. The P is the initial point. And the Q is our terminal point. So this segment has direction going from P to Q. Now, this is different than the line segment Q to P. So the way we would write this, P to Q, we would write P first, then Q, and then a little arrow above it for vector. Now, some books you'll see it as PQ, and you'll have like the little single arrow there. In your book, you will note that vectors are bolded. They're in boldface type. But we're going to actually use another symbol for it.
Italic?
Not italic, because I can't typically write italicized. Yes. No, they're the same. So when you see these two, these will be the same. Now, if we were looking at the vector from Q to P, then this means that your vector starts at Q and it goes to P. These are two totally different vectors. Now, both of these vectors look like they have the same length. They have the same length, but they have different directions. So the vector QP is different than the vector PQ. Now, the length of a vector is called its magnitude. So the length of the vector is called the magnitude of the vector. And the way we symbolize that is kind of with a double absolute value sign. So it's the magnitude. You remember in the in polar we had modulus, and we also had the absolute value. Kind of satisfies the same thing there. It's the magnitude. So this is equal to the magnitude of vector PQ. It is also the distance from P to Q.
Oh, what is that?
And then one of the things that we always want to remember is that distance is always a positive value. I think we talked about this before. If we go out on the track and somebody runs 4 times around one direction, that's 1 mile. Someone runs 4 times around in the opposite direction, that doesn't mean they ran a negative mile. The distance is still positive. Distance is always positive. So because of that, this next point is important. So vectors do not have negative magnitudes. Okay, the magnitude of a vector is always the length of that vector. The length is the distance from its initial point to its terminal point. That is always positive. So in essence, a vector is a directed line segment. So all vectors have both magnitude and direction. They both have magnitude and direction. So the direction is important. A couple of very famous vectors that we deal with kind of all the time, what? Are velocity. The velocity vector and the acceleration vector. Those are some ones that we're going to be working with as we go through. All right, any questions so far? It does. It does. Yeah. All right, now.
This is physics?
No. Vectors, you use vectors in physics.
What the heck?
Rate of change. Okay, so next, let's take a look at a couple of examples. All right, now, let me pause this just for a second. Unpause it. All right, so here, we're going to take a look at 4 scenarios, a vector v, vector w. So with v, 2 vectors can be equal to each other. So let's say we have a vector v here, and it does this. So we'll call that vector v. And typically, like I said, in your book, you'll see your vectors, they'll be in boldface type. So let's say we have this vector here and this one here, and this is w. Now, these vectors are equal to each other. Vector v equals vector w because not only are they the same length, they have the same direction. Okay, so since both have the same magnitude and direction, they are equal. Now, do you notice something about these particular vectors that kind of stands out? They're parallel. Okay? So remember, parallel lines, they have the same slope, different y-intercepts. One of the things that we're going to get to a little later on is we're going to use parallelograms to actually add vectors. So think of that parallel property that they have. So they're going in the same direction, and they also have the same magnitude or length. So these vectors are equal. Whereas in the next example, these vectors they have the same length, but these vectors are not equal. Why are they not equal?
They don't have the same direction.
They do have the same magnitude, but not the same direction. Okay. So vector v is not equal to vector w. Okay, how about in this scenario? Let's say we still have our vector v, but this time here's our vector w. Are these two vectors equal? They're parallel, right? But they have opposite direction. So they also have the same magnitude, but they actually have opposite directions. So the reasoning for example 2 and example 3 are the same. Same magnitude, not the same direction. But in this case, you got to be really careful. So just because two vectors are parallel and they have the same magnitude does not mean that they will have that they will be equal. And our last example. So let's say we have this v here. And that w. So here's another example of two vectors that are parallel. They have the same direction, but in this case, they do not have the same magnitude. Same direction, but not the same magnitude. All right. Well, how do we determine the magnitude of a vector? Yes.
So magnitude is just distance, right? Based on length.
Yeah, so magnitude would be the length of the vector. It would be the distance between the initial point and the terminal point. Yes. By the way, how would you find the distance between 2 points? You would subtract? Okay, so let's say we had something like this. So we have the point 1, 1, and 3, 4. Okay, so how would we find the length of this vector? So you guys said to subtract. So how does that work?
Make a triangle.
You can make a triangle?
Make a triangle and use Pythagorean theorem.
You can use Pythagorean theorem. What's another way? Okay, so if we do that, yeah. But what's another way? It's yes.
Darwin said subtract x2 from x1.
Okay, and then what will that allow us to do? So if we subtract, so here, if we're starting at this point here and we're ending here. So we're starting at 1, 1. So our x value goes from 1 to 3. Our y value goes from 1 to 4. So the distance from here to here, from 1 to 3, is 2. So 3 minus 1 is 2. And the distance from here to here, well, 4 minus 1 is 3. Okay. But before we learned Pythagorean theorem, maybe about the same time, we also learned about something called the distance formula. So our distance formula between 2 points is the square root of x2 minus x1 squared plus y2 minus y1 squared. And that really also serves the same purpose as creating a triangle and using the Pythagorean theorem. They're actually the same numbers. Now, this particular vector starts at 1, 1 and it goes to 3, 4. So the 1, 1 would be 0.1. The 3, 4 would be 0.2. Initial point, ending point. So the magnitude of this vector, we use this symbol here, the double absolute value sign, and that's going to equal to the square root x2 minus x1, so 3 minus 1 squared plus, that's a what? V for vector, yeah, because it's vector v. And then y2 minus y1 squared, so 4 minus 1 squared. So we get the square root of 2 squared, which will be 4, square root of 3 squared, which is 9. So our magnitude of vector v is going to be the square root of 13. Yes.
So when it's just a vector with one letter assigned to it, would you need to put the arrow on top still?
Yes. No. Actually, that's a great question. So the question, if you guys didn't hear, is when you have a vector that has like one letter assigned with it with the v, like this one right here, do we need to put the arrow on the top? And the answer is yes and no. In your book, all of your vectors are in bold-face type. So because they're in bold-face type, you're not going to have the arrow on there. But it's very difficult in our homework and in our notes to write a vector in bold-face type. So what we should be doing is this, because we can't replicate the bold-face type that's in the book. Okay? Good question. All right, so how do we write a vector? How do we represent it? Well, a vector is represented using the letters I and J. So AI plus BJ. I is the horizontal, and J is our vertical.
Why are we using I and J?
Because those are the letters that are used in vectors. And so this is 2 dimensions. So it's IJ. When we get into 3-dimensional vectors, then it's IJK for the X, Y, and Z axes. I think our unit after this one is linear algebra. So you'll see us going from 2-dimension to 3-dimension to 4-dimension and solving problems. All right, so let's say we had vector W equals negative 3I plus 4J. Okay, so how could we graph that? Negative 3I plus 4J. Well, its graph, kind of like when we graphed in the complex plane, where this is our real and our imaginary, except for our I is our horizontal and our J is our vertical. So we would go negative 3I plus 4J so that would be our vector W here. Now, one of the things that we're going to do a little later on, which ties really into our complex and our polar, is we will be able to determine an angle measure from our standard position. Tangent of theta is equal B over A, just like we did in polar, just like we did in complex. All right, so what's the magnitude of this vector W? So we would say W, magnitude of W is equal to the square root. Now, because your initial point is on the origin, so when we do x1 minus x2, it's just really negative 3 minus 0 squared. So negative 3 squared plus 4 minus 0 squared gives us 4 squared. Square root of 9 plus 16. Square root of 25, and the magnitude of vector W is going to be 5. Now, you guys are a little ahead of my Calc BC because they don't start the vectors until tomorrow. And then after that, they're doing polar. So you guys are kind of right in the same spot where they are.
So pre-calc bending is tough.
Well, calculus, you're going to use a lot of the material that we learn in pre-calc. Yes. So all of the stuff that you guys did with polar, they're going to be doing it in a couple of weeks. Parametric we start, they're going to be doing it.
Basically, you got to take pre-calc in order to go to calc.
Do you have to? You should, yes, definitely.
Should.
Oh, yeah, definitely.
But if you don't,
Then you'll struggle. Well, you can struggle a little bit with it if you don't take pre-calc before. All right, so a vector with the initial point at the origin is called the position vector. So a vector who has its initial point at the origin is the position vector.
That's a very creative name. That's a very creative name.
Okay. All right, now add and subtract vectors. Multiply vectors, or not actually multiply vectors, but multiply a constant to vectors. So that's the last part that we're going to do today. Okay, so to add and subtract vectors,
it's going to be long or short?
no, it's not going to be that long.
What if it right here?
No,
So it's long.
it's not long. It really isn't long. Okay, so let's say we have vector v, and that's going to equal to a1i plus b1j, and then we have a vector w, then that's equal to a2i plus b2j. Then if we were to add these two, then v plus w is all you're going to do is combine the like terms. So that's going to be a1 plus a2i, b1 plus b2j. Vector v minus vector w is equal to a1 minus a2i plus b1 minus b2j. Now, here's where we have to be a little careful. Not a little careful, a lot careful. The vector v minus w does not necessarily have to be the same as the vector w minus v. Because the vector w minus v, we said that vector v is a1i plus b1j, w is a2i plus b2j. So if we're going to go w minus v, the w has to come first. So in this case, that would be a2 minus a1i plus b2 minus b1j. So there we have to be really, really careful. Because for the most part, you are going to come out with different answers with the subtraction going one way or the other.
It can never be negative, right?
What? The magnitude can't. The components can.
Oh,
The components can definitely be negative. The magnitude, when you do the square root of x2 minus x1 squared plus y2 minus y1 squared, that will always be positive because you're squaring. Even if it's negative, you're squaring it. When you square it, it makes it positive. So the magnitude can't be negative, but the components themselves can. As a matter of fact, let's take a look at this example. Let's say v is equal to negative I plus 3j, and w is equal to, let's say, 4i and then minus 7j. So what is vector v plus w? Well, we're going to keep our i's together. We're going to keep our j's together. This is an example. So vector v plus w will be negative 1 plus 4i plus 3 minus 7j. So a1 plus a2, b1 plus b2. So that's going to give us 3i and then minus 4j. Now from this new vector, we can find the magnitude of this one. So what's the magnitude of v? We can find the magnitude of w, and we can also find the magnitude of the new vector, v plus w. Now if we were to calculate v minus w, okay, so v is in front, so v goes first, so that's going to be negative 1 minus 4i plus 3 minus a negative 7j. So that gives us negative 5i. 3 minus a negative 7 will be plus 10j, and that's our solution. One more. How about w minus v? Vector w minus vector v. So in this case, the w is first. So it'll be 4 minus a negative 1i. So the 4 minus a negative 1 plus negative 7 minus 3j. So in this case, it's 5i and then minus 10j. Now, do you think, take a look here, seems like these became opposites.
That cannot be applied to everything, right?
That probably cannot. So you can, please don't assume that this is going to happen. Make sure you work the problems out. All right, scalar. Scalar multiples. Okay, so let's say v is equal ai plus bj, and k is a real number. So not a complex number, but a real number. Then
What does it say? And what?
a real number,
Okay.
and k is a real number.
That's okay.
K. Then k times v is equal k times a I plus k times b j. So if you're multiplying a vector by a real number, just multiply both a and b by that number. See, it's not so bad just yet.
Just yet.
I honestly think it's going to be easier than what we just did. So, all right. So let's say we want it. So here we have some vector v. It's 5i plus 4j. What if we multiplied 7v? So if we multiply this vector by 7, then it's going to be 7 times 5i plus 7 times 4j. So our answer would be 35i plus 28j. So that would be our new vector. K is 7. That's our scalar multiple. All right, one more example, and then we're ready to get started on the homework.
Should have last time.
I know, I keep saying stuff that's... All right, here we go. Last example. And I want you guys to try it. Okay, so V equals, so vector V is 5I plus 4J, and vector W is equal 6I minus 9J. So, ladies and gentlemen, what is 4V minus 2W? So what is 4 times vector V is 4... So 4 times the vector V is 4 times 5I plus 4 times 4J. So that's 20I plus 16J, right? 2 times the vector W is 2 times 6I, and then minus 2 times 9J. So that's 12I minus 18J. But we have this negative in between. So 4V minus 2W is going to be, here's 4V minus, so there's 4V minus 12I minus 18J. So this negative sign has to be distributed to both. So that's 20 minus 12I, and then plus 16 minus a negative 18J. So you should have gotten 8I plus 34J. All right, so that will be it. Again, your homework, page 782, 5 through 37, every other odd. So page 782, 5 through 37, every other odd. All right.